Today's lecture will concern uh, mechanics, and there will be other lectures in this series, such as electromagnetism, standard, and so forth, standard outline of an undergraduate physics curriculum, as well as another series of a graduate physics curriculum up to the 6th year, and then a few extensions upwards into the 10th year, as which I have studied to some extent in different ways. For mechanics, I wish to discuss its generalized form. Let's define mechanics as being a system of relating mass to matter to energy, or mass to energy and to time and space. There are different definitions for things such as kinetics, dynamics, mechanics, continuum mechanics, and so forth. We don't have to really worry about those definitions. We're going to plunge right in and consider the elements of such as that we have Newton's laws. A body will continue, continuous state of rest will remain in a continuous state of motion or rest, will remain in that state unless otherwise perturbed, or as well as F equals ma, and the third law being, I believe it's the definition of force being the time rate of change of velocity. This framework was invented in the 1700s by Isaac Newton. It had been extended by Lagrange, Joseph Lagrange, around 1780 to extend to coordinate-free methodologies, which is otherwise known as energy-free methods, in which curvilinear coordinates were accepted. And it's generally much richer than that. It's what a relativist would call generally covariant equations. What the Lagrangian equations look like. It's basically what they define as an action principle, in which the integral of the action is set equal to 0 by energy conservation. Then the energy under the term, the action under the term, as defined as force dot time, the inner product, is defined by a expansion with respect to derivatives while differentiating under the sign for the integral constant. And so what you get is a manipulation of the Lagrangian, which is defined as T minus V, the total energy minus the potential energy. This is readily seen as a very efficient means for calculating very difficult to think about physical situations involving many degrees of freedom or variables or constraints. It can handle all three, such as something in a very large amount of dimensions, or something with multiple constraints, or something with a lot of initial and conditions and velocity, and even stranger conditions, such as Robinson Neumann conditions, partial differential equations. Within this framework, we have also the Hamiltonian, which is something made famous for its role in quantum mechanics, but this also shows up in classical mechanics as a commutator principle, which is null, which is basically the Q dot dot Q dot P is null, meaning the canonical conjugates are null. And this formalism is extended onto other things such as the Jacobi product, the Poisson brackets, and the anti-commutator. But within this richness, we have a complete system that is consistent with Lagrangian mechanics for richness of development within curvilinear coordinates. The Hamiltonian isn't so much known for that. It's known for things that are in which you can swap out easily between conjugates, such as a momentum conjugate onto an energy conjugate, for example, through a derivative. That shows up sometimes in classical problems. Okay, so let's move on to some examples of these problems which we're going to consider with these methods. We have problems of translation, rotation, and both. And we can richly define this as being an O3 operator if we were to look at it from a quantum field theoretical standpoint, but it also serves an equivalent role in Newtonian and Lagrangian and Hamiltonian mechanics. Is that there's an equivalent amount of richness within these systems for solving these problems adequately according to initial value problems, boundary value problems, and mixed conditions. And that there are mathematical methods. It's generally studied in mathematical physics, such as series methods, integral methods like transform methods, variational methods, Galerkin methods such as finite elements methods, finite differences methods, methods involving differential topology. If you really want to get technical, that should be necessary. What we're looking at now is basic, let's call them conditions under which we wish to solve partial differential equations in mechanics. And we find that if a problem may either be defined as well-defined or ill-posed, meaning either as a closed form, no form, or a closed form, a weak form, or no form are the three options, meaning it has a solution, no solution, or many solutions, maybe even an infinite number of solutions thereupon, or recursively thereupon. We see that this methodology, if we're attentive to units, we can select base units in which everything cancels and we're left with only fundamental integers, for example, which, like for instance, units in which gravity cancels with newtons in mass, for example. Equivalently, just similar to what was done in relativistic mechanics, in which mc squared, the Einstein constant, is essentially set equal to 1 for convenience of calculation, since this calculation, indeed the Minkowski radical is used over and over again. A Lorentz contraction radical is used over and over again in relativistic calculations. So we are going to be looking at further at this point the Noether conditions, named after Emmy Noether, the famous, I believe she was German. She lived in the 1800s. She with a very eloquent formalism in Lagrangian mechanics, a set of theorems, conservation theorems, that says that energy conservative systems are necessarily admit a null current divergence, for example. I forget exactly how the Noether conditions work, You can look it up on Google. It's spelled Noether, Noether. Um, it's a fairly eloquent method for devising theorems and calculations concerning problems which exhibit a high degree of symmetry, and also problems which exhibit a high degree of symmetry breaking in a classical sense, like problems which are asymmetric, like which involve for instance, if you're considering a triply coupled spring, 3 springs in a row, coupled to a mass, and you want to know equilibrium conditions, then you have to use a matrix, and if the masses are weighed a certain way and the springs are certain constants, then the system is antisymmetric or symmetric or thuswise, or toplets, or off diagonal or diagonal, or emits eigenvalues of a certain type. So there's this richness within these methodologies for expositure. Formalistic mechanics discusses things such as tensors, if you really get into what is known as continuum mechanics. Those usually use finite elements more, or tensors. It's generally what they mean by generally covariant equations, or consistent equations, or equations that made a current density and or certain boundary value conditions. These conditions are more or less exhibiting the tensile products of the boundary, the stress energy momentum tensor, in terms of the inner tensile strength properties as a three-dimensional time function, where all three variables and time are taken as variant on both sides under the derivative rather, written as F equals ma. And with continuum mechanics, often you see pressure used more often than force. It's more eloquent for that reason, because it redistributes more readily than force does. The force cancels out, but having to write out each term and cancel out the integrals looks kind of sloppy, so we just write a pressure function, and then we have a closed form. I guess that concludes this lecture. I mean, I will conclude it by saying that within certain numerological conditions, such as numerology in its occultist sense, that you will observe strange things even if you apply things like Newtonian methodologies to things such as bodily motions. I generally don't encourage this way of thinking. It's just sort of surreal and or existential or unreal in a way that is psychologically unsettling. We should adhere strictly to mechanics proper. The next lecture will be on electrodynamics, and then the next lecture on optics, and then the next lecture on thermodynamics, the lecture of that on fluid dynamics, the lecture after that on special and general relativity, the lecture after that on kinetic theory of gases, which I know very little about. Have a good day.